Next, section 3.8 talks about implicit differentiation. What does that mean? Okay, so in most math functions, we have our dependent variable y being defined as a function of the independent variable x. And in this case, we'll express y in terms of x. An example of this would be y equals x squared plus 1. And we say we're defining y explicitly in terms of x. Now, what if I have an equation where y is not expressed entirely in terms of x? We say the equation defines y implicitly in terms of x. So, for example, x squared plus y, we would first need to solve for y. Implicit differentiation is a great tool because it allows us to find slopes of tangent lines to curves that are clearly not functions. For example, they're a function if they fail the vertical line test. For an example, here's a circle whose center is the origin with radius 5. And this is a new way for us to find the derivative. So, implicit differentiation, what do? To inform implicit differentiation on an equation that defines a function y implicitly in terms of variable x, we do the following steps. So you take the derivative of both sides of the equation. Next, we need to rewrite the equation so all terms containing the derivative with respect to y are on the left and all terms taking the derivative with respect to x are on the right. And we're going to factor out dy dx on the left. So we should probably do an example. Let me find my example. Here we are. Sorry about that. So here's my example. I have to take the derivative of both sides of this equation. So I have the derivative of the left equals the derivative of the right. Okay? So if I take the derivative of x squared, this is going to be 2x. But now I'm taking the derivative of y. So that would also be 2y. But I need to denote this with a dy dx. This derivative of a constant becomes 0. So I've got 0. The next thing I want to do is I want to get, I need to factor out my dy dx. And I need to then have that be on the left-hand side. So I'm going to subtract 2x from both sides. So I have 2y dy dx equals negative 2x. Next, I need to divide both sides by the appropriate algebraic expression. So I can divide both sides by 2y. That gives me my derivative is x, negative x over y for this first example. Let's go ahead and clear our markings, change colors, and work through our second example. So now I have x cubed sine y plus y equals 4x plus 3. So I'm going to take the derivative of both sides. My right side's easy enough, right? That just becomes 4. This left side's a little trickier, right? Because here I have to use the product rule. I'm going to have to take the derivative of both of these with respect to y. So I have d dx x cubed sine y plus d dx of y. Well, this is just going to become 1, so it becomes dy dx. Here I have to use the product rule. So I've got 3x. I should probably start over a little bit further. This is kind of long. So the derivative of x cubed is 3x squared times sine y plus the derivative of sine y, which is cosine y, to y dx times x cubed. What I'm going to do next is I'm going to subtract this from 3x squared sine y from both sides to get my dy dx by itself. So now I have 4 minus 3x squared sine y equals cosine y dy dx. Let's do x cubed. Moving this to the front. X cubed cosine dy dx. I need to divide both sides by x cubed cosine y. And I've got this 1, right? Oh, I forgot. So I'm going to factor out the dy dx. That means I've got x cubed cosine y plus 1 equals 4 minus 3x squared sine y. And I'm going to have to go ahead and divide both sides by this term right here. So let's make us some more room. This would give me dy dx equals 4 minus 3x squared sine y all over x cubed cosine y plus 1. So how would I then use this skill to find the tangent line at a point? So let's say I have y cubed plus x cubed minus 3xy equals 0 at the point 3 halves, 3 halves. The first thing I need to do is implicitly differentiate both sides. Okay? Once I've done that, I substitute in my point. So I know that if I implicitly differentiate this function, check this for yourselves, I get negative 3x squared plus 3y over 3y squared minus 3x. Now I'm going to substitute it in 3 halves. So if I substitute in 3 halves, negative 3 times 3 halves squared plus 3 times 3 halves over 3 times 3 halves squared plus 3 times 3 halves. This is all going to simplify down to negative 1. This becomes our slope. Now finally we're going to use the point slope form to find the equation of the tangent line at this point. So I have y minus my point, which is 3 halves, equals negative 1, x minus 3 halves. So I get y equals negative x plus 3 halves plus 3 halves. So y equals negative x plus 3 is our final answer. So in order to find the slope tangent lines to a curve at a specific point, the first thing you want to do is use implicit differentiation and then substitute in your point.